Alright, now let's move on to the example for this particular subtopic. So for whole milk, it is being cooled in the pipes of a tubular heat exchanger from 30 degrees Celsius to 10 degrees Celsius by water at 1 degree Celsius. Right? So the cooling medium is cooling water, this one. Okay, and then the milk is being cooled. So our main product that we are going to cool down is our milk. Alright, it is being cooled from 30 degrees Celsius to 10 degrees Celsius. The pipe diameter is 5 centimeter and the milk flow velocity is 1 meter per second. Okay, when we talk about the velocity, the flow velocity of a liquid, if the velocity of a liquid, velocity of fluid, alright, is greater or equal to 1.0 meter per second. So this one, we can consider that the flow of the liquid is turbulence. Alright, this one you are going to learn it further in chapter 7 about the flow properties of a fluid. Okay, and then if let's say the velocity of fluid is less than 1.0 meter per second, then this one we can categorize the flow of velocity as to be laminar flow. Alright, so in this case, for this particular example, the velocity of the milk is 1 meter per second, meaning that this particular flow has been categorized into turbulence flow. Alright, it's turbulence flow. So calculate the heat transfer coefficient. So you need to calculate the heat transfer coefficient. This is your task for this particular problem statement for the milk by using the following physical properties. Alright, these particular physical properties, this particular density, Cp, thermal conductivity, as well as mu, the viscosity, this one are been given to you based on a table. There is a table, specific table that is meant for a certain type of fluid. And can you see here that all these values, the rho, Cp, K and mu, they are being measured at mean film temperature. Okay, mean film temperature is whereby the mean film temperature for the milk. Okay, so what is the mean film temperature? You need to calculate for the average of the liquid, average temperature of the liquid. Alright, so this one will be 30 degrees Celsius plus 10 degrees Celsius divided by 2. So you get by 20 degrees Celsius. Okay? Alright, but then this one you don't have to calculate because normally this particular value, the rho, Cp, K and mu, they are going to be given to you and you need to know how to use it. Alright, but then one thing for sure, this particular equation, in this particular problem statement, this particular equation is being given directly to you. But in a real situation for problem statement, you are going to be given a selection of equation. Okay, selection of equation. You need to select which one of the equation given to you is the most appropriate for the problem statement. Alright, so why this particular equation, Nusselt equals to 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33 is been given to you, because this one you need to refer back to the previous slide whereby it is meant for the liquid flow, whether it is a laminar flow or it is a turbulence flow, and whether it requires heating or cooling process. So which particular slides that I'm talking about? Alright, so you need to move back to the previous slides. Alright, so this is the slide that I'm talking about for forced convection equation that is referring to the problem statement that we are working right now. Okay, so this particular equation is meant for heating and cooling inside tubes for the pipe, and this one, it refers for the temperature difference for the cooling or heating process, reasonable long tube. Alright, if let's say the fluid flow at laminar flow, meaning that laminar flow is less than 1 meter per second. Alright, so you need to use this particular equation. Nusselt equals to 1.62 times by Reynolds times by Prandtl times by diameter over length, okay, to the power of 0.33. But if let's say the flow of the fluid is greater or equals to 1 meter per second, then you need to use this particular equation. Nusselt equals to 0.023 Reynolds to the power of 0.8 times by Prandtl. Alright, this one to the power of n. And this particular n, it depends on the process that involved for the fluid that we are working with. If let's say the process is heating process, then you need to replace the n with 0.4. But if let's say the process is meant for cooling process, then you need to replace the n is for 0.33. Alright? So for our case just now, for the problem statement that we are working with, that particular process is a requiring cooling process. So when it is a requiring cooling process, then we need to use this particular equation as 0.33. And again, this particular equation, these two equations will be given to you, but you need to select which equation that you need to choose. Okay, so the first one is you need to choose the most appropriate equation. Okay, choose equation. And number two, if let's say you choose for B, if let's say you choose B equation, then you need to select for the value of n value. Okay, whether it involves with heating or cooling process. So you need to be smart in order for you to select which equation that is the most appropriate to settle for the problem statement. Okay, now so we are back on this slide for this particular problem statement. Now let's move on for, okay, so for the Nusselt equation, we have selected that it is a requiring cooling process. This one is the value of the n. This is cooling process. And the Nusselt equation that we are choosing is Nusselt equals to 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. Alright, since you have selected the equation, now let's move on for the problem solving. Okay, so for this particular mean bulk temperature, this one I have mentioned just now, this one is meant for the milk. Okay, and this particular 20 degrees Celsius is meant to find for the physical properties of the fluid. So it is not necessary for you to look for these particular values because the values of physical properties will be given to you. Okay, for example, you have the Cp, you have the mu, you have the rho, and then Sk. So this one normally will be given to you in the problem statement. Alright, so you don't have to calculate for this one. Okay, and then this one is just an additional information to you. If let's say the Reynolds number is greater than 10,000, then viscosity should be measured at the mean film temperature. So mean film temperature is 1 plus half. Okay, half is because this one we are looking for this particular average temperature. Okay, divide by 2 equals to 10.5 degrees Celsius. Again, this particular value is to look for the physical properties. Okay, so for milk, can you see this one? Milk at 10.5 degrees Celsius. Okay, this physical properties mu is at this particular value. Right? It is not going to use this particular temperature when we are talking about the mu, the Cp, the density, and etc. because you need to calculate the value for Reynolds first. When you calculate the value for Reynolds, it is greater than 10,000, then we need to use the mean film temperature. 1 degree Celsius, this one is the cooling water, the temperature of cooling water. Alright, so okay, so this particular physical properties will be given to you, so you don't have to worry about this. But what you need to do is that you need to solve the problem. Okay, so the first thing what you need to do is first step, you need to calculate for the value of Reynolds. And again, this particular equation you need to memorize. Okay, Reynolds equals to dV rho over mu. Okay, D when it involved with diameter. Right, since this one we are talking about tubing, then it involved with diameter. V is the velocity, rho is the density, then mu is the viscosity. Viscosity has been given to you. So you calculate the value of Reynolds, and one thing, Reynolds, Prandtl, and Nusselt, they are dimensionless. Dimensionless meaning that they have no unit, because all of the unit has been cancelled out. Okay, you can try to put the unit over here in each of this value, then you can see that all the units will be cancelled out, whereby you will leave with no unit at the end of your answer. Okay, so when we calculate the value of Reynolds, Reynolds equals to dV rho over mu, then you replace with all the values that you can find from the problem statement, from the value given in the problem statement, then you will get the value of Reynolds is 18,393. Okay, and then the second step, what you need to do is you need to calculate for the value of Prandtl. And again, this particular equation you need to memorize as well, because this particular equation is not very complicated for you to memorize. So Prandtl equals to Cp mu over K. So just plug in all the values that has been given to you into the equation. Okay, so when you calculate the Cp mu over K, then the value of Prandtl is 19.5, and again, this particular value has no unit. And last but not least, you need to calculate for the value of Nusselt. Nusselt equals to HCD over K. Okay, this one is the general equation of Nusselt, and this particular equation you need to know. But from the selection of the equation that you have selected just now, you know as well that Nusselt also is equals to 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So what's happening here is that one, Nusselt equals to HCD over K. And Nusselt is also equivalent to 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So this one is Nusselt, this one is Nusselt. They are equivalent. Okay, so what's happening here is we are going to look for the value of Hc. Okay, again, can you refer to the previous slide whereby you need to calculate for the heat transfer coefficient. Alright, so in order for you to calculate for this Hc, the value of Hc, so what you need to do is that you equalize the equation of Nusselt equals to HCD over K with Nusselt equals to 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So what's happening is that you just equalize. So one is Nusselt, HCD over K equals to this one also Nusselt, 0.023 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So can you see here, this one on your right hand side is equation for Nusselt, on your left hand side this one also is equation for Nusselt. So that's why you can equalize both of this equation, and from this particular step you can look for the value of Hc. So that's why you can see that this particular equation here has changed to become Hc equals to 0.023 times by K over D times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So this particular D and K, you move it to the other side because we are looking for the value for Hc. So when you calculate for the value of Hc, then you should be able to get the value of 1768 watt per meter square Kelvin. Alright, so this particular question, normally I am interested to include this particular question in one of your tests or quiz or maybe the final exam papers, because this particular problem statement, it is not that difficult, but you need to think, how can I calculate the value for HC? Okay, and this particular unit also is important for you to write it down properly, because all the units has been given to you from this particular problem statement. They are being given to you, so you need to know how to cancel out and where the unit will lies. Okay, so basically the unit coming from this one, K over D. Because as I mentioned just now, Reynolds is dimensionless, Prandtl is dimensionless. So only left with K over D that is having with unit. So that's why at the end you will have the unit of watt per meter square Kelvin. Okay, so this is the problem solving for the question that has been given in previous slide. Alright, then we move on for the heating or cooling over plane surface. Plane surface meaning that this one is a flat surface. Alright, for a plane surface, the problem of characterizing the flow arises as it is no longer obvious what length to choose for the Reynolds number. The length of the plate measured in the direction of the flow is taken for D in the Reynolds number, so that the value of the equation for the nacelle equals to 0.036 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33 if the value for Reynolds is greater than 20,000. Okay, so what does this particular statement means is that now we are talking about flat surface. For flat surface, you don't have diameter. Okay, there is no diameter. Instead, since we have the equation Reynolds equals to dV rho over mu, since we don't have this particular diameter, so what's happening here is that the diameter, is going to be replaced with the length of the tube. So it becomes LV rho over mu. Okay, L is the length. So you need to know what is the surfaces, what is the material that you are working with from the problem statement given to you, whether we are working in a tubing or we are working with the flat surface. Alright, and then after that, when you are being given with problem statement, the first thing what you need to do is you need to calculate for the value of Reynolds. Okay, when you calculate the value of Reynolds and the value of Reynolds is greater or equivalent than 20,000, then you can choose to use this particular equation. Alright, so for the flow of air over flat surfaces, the equation can be simplified as below. HC, okay, the heat transfer coefficient, HC equals to 5.7 plus 3.9 V. V is the velocity. If let's say the velocity of the air, okay, now we are talking about the velocity of air, is less than 5 meter per second. But if let's say the velocity of this one, okay, this one is a velocity is greater or equals than 5 meter per second, but it is lesser than 30 meter per second, then you need to use this particular equation of HC equals to 7.4 times by V to the power of 0.8 for this particular situation. Okay, V is less than 30 meter per second, but V, the velocity of air, is greater or equals to 5 meter per second. Okay, so this particular equation nacelle, and then if you are looking for the value of heat transfer coefficient, can be applied only for smooth plates. Okay, values for HC for rough plates basically are higher because there are some resistance when the fluid is going to flow on a rough surface. Alright, so now let's move on for a example, the next example. Calculate the surface heat transfer coefficient. So again, this is your task. The first statement is your task. Okay, you need to calculate for the value of HC. Calculate the surface heat transfer coefficient to a vegetable puree which is flowing at an estimated 3 meter per minute. Alright, this one is just to trick you, this particular value, 3 meter per minute. So this one is meant for the velocity. Velocity is 3 meter per minute. Alright, whereby normally velocity is being expressed as meter per second. So what you need to do is that this particular minute you need to convert the unit to become second. Alright? Okay, so this one, when the example given to you, when the question given to you, you need to pay attention to the units, to the values, and all the parameters that has been given to you. Okay, the fluid flow, okay, the fluid is flowing at 3 meter per minute over a flat plate. Alright, so this one is a flat plate. So you need to know, again, this one flat plate, this is not going to be tubing. So we are going to deal with flat plate. So it should be immediately occur in your mind that when you are talking about flat plate, then I need to deal with the length of the plate. We are no longer going to work with the diameter. Alright, so flat plate with 0.9 meter long by 0.6 meter wide. Okay, if steam is condensing on the other side of the plate and maintaining the surface which is in contact with the puree at 104 degrees Celsius. Okay, this particular steam temperature is at 104 degrees Celsius. Assume that the physical properties of vegetable puree are being given. You have the density. Okay, so you need to know density is being using which particular annotation. Okay, so this one density is rho, and then specific heat is K. Then you have the specific heat is Cp. Then you have the viscosity is mu. Then you have the thermal conductivity is K. So you need to know, for density is being denoted by rho, and then viscosity is mu. I have experience from the previous students whereby they are mistakenly for this particular density and viscosity, whereby they put density value as the mu and they put the viscosity value as the rho. So when you put into the equation for the Reynolds number, for Prandtl number or Nusselt number, then it will be wrong because you have mistakenly changed the values that has been given to you. So you need to know which denotation is appropriate for the physical properties that has been given to you. Alright, so those parameters has been given to you and you need to know which part that you need to pay attention to. Alright, so for example, this one, what's happening is that I have a flat surface like this. Alright, the length of the flat plate is 0.9 meter, 9 meter long. Okay, and the width is 0.6 meter. Alright, this one, we are not going to pay attention for this one because it does not reflect anything. But this particular length is the most important thing because you need to use this particular value in the equation. Okay, and then the steam passing on the other side, the temperature is 104 degrees Celsius. Okay, so now let's solve this particular problem. Alright, so I have mentioned just now, since we are dealing with a flat surface, then you need to use the equation of Reynolds equals to L V rho over mu because we are talking about flat surface. Okay, and then you just plug in all the values, 0.9. Okay, 0.9 is the length and velocity is 3 meter per minute. Okay, can you see that here 3 meter per minute? This particular 60 is meant for 1 minute is equivalent to 60 seconds. Alright, so it is just like this, 3 over 60, because you are going to get the value of V equals to the answer meter per second, because at this moment this particular value is meter per minute. You want to convert the unit from minute to second. Alright, then you times by 1040, this one is the density, okay, over mu. This one is the value for mu, and this particular 60 is meant for you to convert the unit for minute to second. Alright, so when you calculate the value of Reynolds, Reynolds is greater than 20,000. This one is 20,000. Okay, it is 2.34 times by 10 to the power 4. So when the Reynolds value is greater than 20,000, then we can use the equation of Nusselt equals to 0.036 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. Okay, because this particular condition, this set of condition has been sufficed. Okay, in order for you to use this particular equation, the Reynolds number should be greater than 20,000. This one has been explained in previous slide. Okay, and then again, Nusselt, and this one also Nusselt, as I mentioned just now. Okay, since we are talking about flat surface, then the diameter is being replaced with length. So Nusselt equals to HCl over K. And Nusselt also is equals to, from the one that we have chosen here, 0.036 times by Reynolds to the power of 0.8 times by Prandtl to the power of 0.33. So equalize both of these equations, Nusselt and Nusselt. So that's why you will get HCl over K equals to 0.036 times by Reynolds to the power of 0.8 times by Prandtl to the power of, Prandtl 0.33. Okay, clear? So can you see how this particular equation is being obtained? Okay, so for Prandtl, okay, you need to calculate for the value of Prandtl. Why you need to calculate the value for Prandtl? Because in this equation you have the value for Prandtl. Okay, Reynolds you have calculated just now. Okay, so Prandtl is equal to Cp mu over K, and then when you calculate the value, just plug in all the values Cp mu over K, so you will get the value of Prandtl 15.3. So from this particular problem statement, again we are looking for the Hc. Okay, again this one we are looking for the Hc. So L over K, just bring it over here. Okay, when you transfer to the other side, of course L will be at the bottom, okay, per L, and K will be at the top. Right, when you put it over here. So just plug in all the values that has been given to you and times by K over L. So you will get the value of 160 joule per meter square second degree Celsius. Okay, where does this unit come from again? This one, Reynolds and Prandtl, they are dimensionless. The only unit that you can get is from K over L. Alright, so this particular parameter, K over L, that contributing to the unit of this Hc, the value of Hc. Alright, are you clear? Okay, so now let's move on to the next one. Heating or cooling outside tubes such as water chillers or chilling sausages, whereby Nusselt equals to K. Okay, K is depends on a certain values times by Reynolds to the power of n times by Prandtl to the power of m, where n and m, it varies with Reynolds number. Okay, so you need to calculate again Reynolds number when you are talking about tube. This one again, you are going to use equation Reynolds equals to dv rho over, okay, Reynolds is equals to dv rho over mu. Alright, we are talking about tubes. Then tubes, you have the diameter. Okay, for gases and liquids at high or moderate Reynolds, meaning that high or moderate Reynolds, the Reynolds value should be greater than 200. Okay, high or moderate Reynolds number. So in order for you to use this particular equation, the Reynolds value should be greater or equals than 200. For liquids at low Reynolds value, whereby the Reynolds is in between 1 until less than 200, then you need to use this particular equation. Nusselt equals to 0.86 times by Reynolds to the power of 0.43 times by Prandtl to the power of 0.3. Okay, so fluid properties in these forced convection equations are evaluated at the mean film temperature, which is the arithmetic mean temperature between the temperature of the tube walls and the temperature of bulk liquid. So the fluid properties, the physical properties such as the K, Cp, mu and rho, this one are being using mean film temperature. Okay, and basically this particular value will be given to you, and this particular statement is just to inform you where does the values, these physical properties values coming from, so that you are not going to confuse yourself. Okay, so for me it is not necessary for you to calculate for the mean film temperature for the problem statement given to you, as this particular physical properties will be given. But then if let's say you go out and you join the industry, then you need to do some calculation for these particular problems, then of course you need to know how to calculate the mean film temperature. Okay, so problem on heat transfer by convection, whereby this one again we are going to use the Nusselt and Prandtl number. Water is flowing at 0.1 meter per second across a 8 centimeter sausage diameter at 75 degrees Celsius. Okay, so this one is the velocity. Water is flowing, so this is velocity. How do you know this is velocity? Because we look at the unit, meter per second, across a 8 centimeter sausage. Alright, so this particular water, it passed through sausages, and the diameter of the sausage is 8 centimeter. Alright, but then this particular unit is in centimeters, so you need to convert from centimeter to become meter. Okay, the temperature is 75 degrees Celsius. Is the bulk water temperature is 25 degrees Celsius. Estimate the heat transfer coefficient. Heat transfer coefficient, you are going to calculate for the value of Hc. Okay, so this particular temperature is for you to calculate for the mean film temperature in order for you to get the physical properties. But again, I have mentioned to you, this particular physical properties will be listed out and given to you. Okay, but what you need to know is you need to know the equation of Reynolds, okay, Prandtl, and then Nusselt. This particular three is very important for you to know this the equations. Okay, so how are you going to select the equation? This one again depending on the condition. So you again for this type of equation, you are going to have choices, several equation. Okay, and you need to select which equation is the best that suits the problem statement. Okay, so in order for you to select the equation, the first thing what you need to do is you need to calculate for the value of Reynolds number. Calculate the value of Reynolds number. When you calculate the value of Reynolds number, then you can know whether the value of Reynolds number is fall under the category of high or moderate Reynolds number, or it belongs to the category of low Reynolds number. Okay, so from this particular problem statement, alright, so the first thing, I have listed out all the values, the physical properties that has been given, and then the first thing what I need to do is I need to calculate for the value of Reynolds. Okay, when I calculate the value of Reynolds, it is a 1.71 times by 10 to the power of 4, meaning that this one is already greater than 200. So when it is greater than 200, that's why we are using this particular equation. Okay, Nusselt equals to 0.26 times by Reynolds to the power of 0.6 times by Prandtl to the power of 0.3. Okay, so after that, you need to calculate for the value of Prandtl. Okay, Prandtl equals to Cp mu over K, and you will get the value of Prandtl. Right, and then you need to apply